Hello everyone, welcome back to Everything Swift. Today we'll be tackling Leetcode question 1382 titled Balance a Binary Search Tree. We're given this root tree node here in this parameter and we're supposed to return a binary search tree that is balanced, right? So the definition of balance in this question is basically if the depth of the two subtree of every node never differ more than one. Basically, the level of it is never more than one, and I think the best way to understand it is through the example shown here. So if we are given this original tree, which is in this parameter here, which is 1, 2, 3, 4, right? And the balanced version is 2, 1, 2, 1, 3, 4. So this is the balanced binary search tree, right? So one of the characteristic of a binary search tree is that everything towards the left of the current node has to be smaller than it. So for example, 2, everything towards the left has to be smaller. So 1 is smaller than 2, that's great. 3 is bigger than 2, but everything towards the right of 2 has to be bigger, right? So 3 is bigger than 2, 4 is also bigger than 2, 4 is also bigger than 3. So that is a valid binary search tree. In the event, for example, like this number here, 4, imagine it to be like 1 or 2, that is invalid because 2 is smaller than 3, but 2 is also right of 3, right? That is supposed to be bigger, right? So at every point in time, at every node, everything towards the right of every node has to be bigger, everything towards the left of every node has to be smaller. So that's one thing to keep in mind, right? So one thing that we can see from this example here, the interesting thing is that uh, this is a valid binary. This is a valid binary search tree as well because it's 1, 2, 3, 4. But they want it to be converted into a balanced version, right? So if we take a look at this, right, this is actually a sorted. Is sorted, right? 1, 2, 3, 4. So it's sorted in ascending order, and how do we construct a balanced version out from this thing, right? So one key observation or thing that we can sort of like pull it out from our head, from our memory, is that if there's anything related to sorted, right, we should probably be thinking about binary search, right? Most of the time, the solution will be somewhere around there. If it's a sorted array or something is sorted or given the order is sorted, like those kind of key, like we should try and apply and think whether binary search can help us out with this problem, right? It's not always the case, but most of the time that is the key tip that we need to pay attention to. If the yeah, like anything that's sorted, like we should try and think like, okay, can binary search help us out here, right? So in this case, it is going to help us out to construct a balanced binary search tree using binary search, right? So I'm going to display it in code, and let's see how that works. So I'm just going to check if root equals to nil, return nil. In the world of Leetcode, this probably would not happen because they want us to solve the problem. But in a real world scenario, like if the root happens to be nil, which is optional here, so it could be nil, we just exit out from this whole function block for performance reason because we have nothing to compute further, right? And now what I'm going to do is I'm going to create a function here called in-order traversal, right? I'm going to traverse this tree here, tree node here, in an in-order fashion, right? So there are three traversal type for tree node, right? In order, pre-order, and post-order, right? It's just referring to the position of the root, right? So in order is basically going towards the left, traverse all the way towards the left, and then traverse the root, and then traverse the right, right? So it's in order because the root is the middle one. in the pre-order traversal is basically root, left, right. If it's post order, it'll be left, right, root. So it's basically referring to the position of the root. That's how they define like whether it's in order, pre-order, or post order, right? So let's try this tree node, and then we'll return a tree node here. Actually, no, I'm not going to return this. I'm going to pass in a parameter here. I'm just going to call these results, and it's going to take an array of tree node. I'm going to make this in out so that we can manipulate this variable here instantly, right? So as with all in order traversal, I'm going to do it in a recursion manner. This probably just take this if root equals to nil, return, and here what we can do is in order traversal root left and results, right? So we're traversing all the way to the left, right? Remember, in order traversal is basically left, root, right? So we're going to traverse all the left nodes, right? And then what we're going to do is append the tree node, right? The current node. Yes, we can take this and then in order traversal root, right, and results. So this is basically our in order traversal in a recursion manner, right? So let's go and create this parameter here and call this tree node. Yeah, and what do we do here? In order traversal root and then results. So this symbol here is basically required because we are declaring it as in out, and in out is basically allowing us to manipulate this variable here in the scope of this function, but the only requirement is that it has to be a variable. It cannot be a constant, right? So I'm just doing this. So after this in order traversal is done, these results will have the tree node inside an array, basically this entire tree in an in order fashion, right? So to construct the balanced version out from this array, we are basically going to use binary search here. And let's try and do this build, and then we're going to pass in the results here, which is tree node. Going to create a start index and ending, start end and in here, and then return the tree node here, right? So just for boundary checks here, if start is bigger than end, that's not good, right? Start has to always be less than end. So in the event if it does happen, we're just gonna exit and return here. So the key thing about like binary search is we have to find the midpoint, right? That's how binary search works. So we're going to calculate the mid, and then start and minus start divided divided by 2, right? So the reason why we are doing this instead of just like and start divided by 2 is because we have to deal with integer overflow. So this is the formula that sort of tackles the issue of integer overflow. So now that we get the mid node from this results array, we're just going to build from that node, right? So here we're going to call it mid node equals to result mid, and this basically gives us the tree node that is in the middle. And then here we're going to do a traversal, right? Mid dot left equals to build, and then we pass in the results, and our starting point is from index 0 because we are constructing the left version, right? So it has to be 0 of the results array, and the ending will be basically everything before the midpoint, right? Makes sense, right? Because like we are basically taking everything towards the left, excluding the mid. So 2 is the midpoint here, right? So we are, in this example, is just 1, right? And then the right is basically everything towards the right of this particular midpoint. So what do we do here is basically build result, and then mid plus 1, and then the n is basically n. We can start here, I guess. And that should be the solution if we return this, right? Let's go ahead and call this here return build results 0 and n. Basically that should be it. Oh no, not n, sorry. Results got count minus 1, right? Minus 1 is basically because we are dealing with index. um, we are going to access the index of the array, so we're just passing the minus 1, so it's a 0 base index. But yeah, so basically to summarize, we are going to do the in-order traversal, right, to build sort of like this mechanism here. So we are doing the in-order traversal first, and then we are going to build the balance tree in this binary search mechanism here, as we can see here. So if it helps, let me just try and print out the mid node value so that you can see it in action. uh, and let's go, right? There we go, 2134, right? 2134, right? So and it's also accepted, so that should be good. But yeah, let me just submit this since it passed the test, and hopefully that works. There we go. We did pass, success. That's the answer for this question. So yeah, in-order traversal, and then we build it using a binary search here to construct this balanced version. So yeah, as always, if you guys find this kind of video helpful, feel free to subscribe to this channel. I'm trying to build put out more content for this channel, and as always, thanks for watching. Take care and bye bye.